Okay, so this will be the first lecture out of chapter 6. So this chapter covers what's known as the SN1 and SN2 reactions. So it's a different mechanism for how reactions occur. And so these are reactions of alkyl halides. So for example, if we had methyl chloride and we took that and reacted it with something like sodium hydroxide, then what comes out of this reaction is CH3OH, so methanol plus sodium chloride. Okay, so let's go through how that reaction occurs. So this reaction is what's known as follows what's known as an SN2 mechanism. So what happens in this reaction? So if we assign partial charges, so chlorine is partial negative, right? And carbon is partial positive because chlorine is more electronegative than carbon. And so if we take that and react that with hydroxide, well, oxygen is fully negative charged. So negatives, of course, are attracted to positives. So what's going to happen in this case is we're going to take a lone pair of electrons on oxygen, and we're going to make a bond to that carbon. So that's carbon's already got 4 bonds, so that's going to put 5 bonds on carbon, and you can't put 5 bonds on a carbon atom, so you have to break a bond. So we have a choice of breaking a carbon-hydrogen bond or a carbon-chlorine bond, and the bond that gets broke is the chlorine. So what happens is chlorine leaves. So using arrows like this is trying to illustrate a mechanism for the reaction, trying to push electrons basically to show how a reaction occurs. So basically this arrow means we're taking a lone pair on oxygen, and if you notice the arrow ends up on the carbon atom, that means we're taking those 2 electrons and we're going to use them to make a bond to carbon. And if you notice this arrow starts on the bond, that means we're taking those 2 electrons in the bond, and the arrow ends on the chlorine atom, means we're making a lone pair of electrons out of those 2 electrons. So we can sketch then what's known as a transition state. So we use a dotted line to illustrate the bond that's breaking. And then we'll use a dotted line. Let's draw a butter dotted line in that to illustrate the bond that's making. And then that's typically put in brackets with this symbol, with this dagger. And so that represents a transition state. So it's a real species, but not in the sense that you can't isolate it and stick it in a bottle because it has a very, very short lifetime in the order of femtoseconds. So what happens then is you finish making the OH carbon-oxygen bond and finish breaking the carbon-chlorine bond. And so now the OH is attached to the carbon, and the chlorine has left, and it had 3 lone pairs to begin with. Now it has 4 lone pairs, so it's negatively charged, so it's a chloride anion. And then we also had a sodium, and the sodium basically didn't do anything in the reaction. So the Na plus is still there, so you have a sodium chloride side product. And then this would be the major organic product. So that type of mechanism is what's known as an SN2 mechanism. So the SN2, so the S stands for substitution. So ultimately we did a substitution, right? The OH substituted for the chlorine. And then the N stands for nucleophilic. So nucleophile, so phile would be to love, so something that loves nuclei. And so a nucleus is positively charged, so this is basically something that likes positive charges. So the OH, so the oxygen is negative, so it's going to like positive, so it's going to be attracted to the carbon that's partial positive. And the 2 stands for bimolecular. So if you remember from General Chemistry 2, what bimolecular means, so it's a second, so this is a second order reaction. And so if we wrote the rate law for this reaction, rate equals some constant K times the concentration of nucleophile, which in this case is hydroxide. So rate equals K times the concentration of hydroxide times the concentration of the alkyl halide. And so in this case, it's CH3Cl. So if you remember rate laws from General Chemistry 2, so the exponent here is 1 and 1. And so if you sum those exponents up, it's a second order reaction. So a bimolecular reaction, it depends on 2 things. It depends on the nucleophile and the halide. So we're not going to be doing any calculations with kinetics. You just basically need to know that an SN2 reaction is a bimolecular reaction, and then understand at least the basic math, like what would happen if we double the concentration of this, and if we double the concentration of this, then how would that change the rate overall? So always, if it's not obvious to me, I always like to just plug in numbers. So K is a constant, so let's just say the concentration of hydroxide and chloromethane was 1 molar. And then if we double the rate, or double the concentration of both, so let's say it was 2 molar and 2 molar now, then that's 4K, and this is 1K, and the K's cancel, so it's 4 times as fast. So if you just double the concentration of the nucleophile, that would double the rate. If you double the concentration of the alkyl halide, that would double the rate. If you double both, that would quadruple the rate. Or if you triple both, then the reaction would be 9 times as fast. Okay, so that's one characteristic of an SN2 reaction. So in the SN2 reaction, then this is what's called the leaving group. So highly technical term, why is it called the leaving group? Because it left. And so we'll see in this chapter, halogens are very good leaving groups. So it could be chloride, it could be bromide, it could be iodide. Okay, so we'll keep track of the characteristics. So 1, the rate of an SN2 is equal to some constant K times the concentration of the nucleophile times the concentration of the alkyl halide. Okay, so let's see. So leaving groups. So the ones that we'll typically look at will be like iodide, bromide, chloride, and iodide's a better leaving group than bromide, which is a better leaving group than chloride. And the reason behind that, so Ci bond is weaker than the CCl bond, and I minus. So I minus is more stable than Cl minus. Okay, so let's just leave some space. So there's some other characteristics that we'll look at for SN2. And I'll try to come back up as we cover those concepts and fill in this the rest of this basic characteristics of an SN2. So let's take so we have this reaction, and then let's compare it to, so rather than methyl chloride, let's say we had tert-butyl chloride. And we let these both react by an SN2 mechanism. So then you need to take a lone pair of electrons on hydroxide, make a bond to carbon, and kick off the chlorine, right? Okay, so, well, so we did actually cover another concept already. So this is an SN2 is what's known as a concerted reaction. What that means is everything happens at the same time. So you made a bond from the nucleophile to the carbon, and the leaving group leaves all in the same step, so it's a one-step reaction. All right, so you go through a transition state and straight to product. So let's move this down and illustrate that. So if we wrote a reaction coordinate diagram for an SN2 reaction, so you have your starting material, and then it goes through some transition state, and then it goes on to products. So that's the transition state. So it's a one-step reaction. That's a characteristic of an SN2. Okay, now let's compare these two reactions. So does one of these look like it should be easier to happen than the other? So keep it in mind that in order for the SN2 reaction to work, the nucleophile has to attack carbon and kick off chlorine all at the same time. And so the problem with this reaction is these methyl groups create, so let's just call them R groups, alkyl groups. So the alkyl groups create steric hindrance to nucleophilic attack. And so what that's basically, the result of that is going to be that this reaction is much slower and this reaction is much faster. So in terms of rates of SN2 reaction, so methyl, primary, secondary, tertiary. So this of course would be a methyl halide, and this would be a tertiary alkyl halide. So the methyl halides, so if we assigned a rate of reaction for the secondary of 1, then primary alkyl halides react about 50 times faster, and methyl halides react about 1,000 times faster, and tertiary alkyl halides react about 1,000th times slower. And so in essence, SN2 reactions don't work at tertiary centers because there's too much steric problems. So that's another characteristic of an SN2 then in terms of the alkyl halide. Methyl reacts faster than primary, reacts faster than secondary, which reacts faster than tertiary, and generally tertiary alkyl halides do not do SN2 reactions. Okay, so another characteristic of an SN2 is the strength of the nucleophile. So some nucleophiles are better than others. In order to study this, basically what you would do is just change out the nucleophile to something else. So if we had a variety of different nucleophiles, so maybe it's iodide, maybe it's an conjugate base of an alcohol. Maybe in water molecule. So again, the basic SN2 is the same. You take a lone pair of electrons on the nucleophile, make a bond to carbon, and you kick the leaving group off. So you do a substitution. So in this case, you would make methyl iodide, or if this oxygen attack the carbon and displace the bromine, then you would make an ether. So if you just set up a reaction with methyl bromide or methyl chloride, methyl iodide, doesn't matter, and just did the reaction with a bunch of different nucleophiles and then measure the rate of the reaction, well, the only thing that's changed is the nucleophile, so then you can get a feel for which nucleophiles react really fast and which nucleophiles react really slow. So for an SN2 reaction then, well, or just in general in terms of nucleophilicity, so nucleophiles like water, carboxylic acids are very weak nucleophiles. And so nucleophiles like bromide, chloride, fluoride, amines, are moderate nucleophiles. So they react at more intermediate speeds, and then you can have good nucleophiles and very good nucleophiles. So again, very technical terms. Okay, so good nucleophiles, something like the conjugate base of a thiol. Iodide, really good nucleophile, very good nucleophile, something like a N3-, which is called azide. Cyanide is a good nucleophile. So for SN2 reactions, you typically have a really good nucleophile, good or very good nucleophile, and as we'll see when we talk about the SN1 reaction, they typically have a very weak nucleophile. And then the moderate nucleophiles could do SN1 or SN2, and it depends on what the other conditions are in the reaction. Okay, so for an SN2 reaction, you generally have a very good nucleophile, and so you just have to memorize what are good nucleophiles, what are not good nucleophiles. So we could put SH on this list as well. Okay, so another characteristic. Well, let's just look at a few examples right quick to get you accustomed to predicting products for these type of reactions. Let's stick RO- on here. So we should stick hydroxide on here. And conjugate base of an alcohol, RO-. Okay, so that's what azide is. That is N3-. So if we took this alkyl halide, so chlorocyclohexane, and react it with azide, so it would typically be something like sodium azide, potassium azide, but the cation doesn't really matter. What matters is the nucleophile, because the cation is just a spectator ion, so it's just watching the reaction. So what happens in this reaction? So first of all, let's convince yourself that this fits the characteristics of an SN2. So how would you classify the alkyl halide? So that's a secondary alkyl halide, and that's a good nucleophile. So we'll just say good and very good. Those are, we'll just call those good nucleophiles for SN2 reactions. Okay, so those two things, that's a recipe for an SN2. So what happens in this reaction is just take a lone pair of electrons on the nucleophile, make a bond to that carbon because that carbon's partial positive, right? And chlorine's partial negative, and lose the chlorine. So you always substitute, and the nucleophile always ends up where the leaving group was at. So for an SN2 reaction. As we'll see, that's not always true for SN1 reaction. So for azides, you could write the Lewis structure out, or you could just simply write N3. That's perfectly fine. Okay, so for this next reaction, so classify the alkyl halide. Make sure it's not tertiary because tertiary can't do SN2. So methyl primary, secondary can. So if you classify the alkyl halide, that's a primary alkyl halide, and RO minus is a good nucleophile. So if you notice, most of these good nucleophiles are all charged. They all have a negative charge on them. And whereas the weak nucleophiles are generally neutral. Okay, so what you want to recognize is that is a nucleophilic atom. Because it's the one that's negative charged. And in this molecule, the carbon is partial positive charged. So the oxygen is going to be attracted to the carbon. So you're just going to take a lone pair of electrons on oxygen, and you're going to make a bond to that carbon, and you're going to take the carbon-chlorine bond and make a lone pair on chlorine. So if we wanted to write the mechanism, then we would sketch the transition state. Okay, so we're going to break the bond to chlorine, and we're going to make a bond to oxygen, and the CH2, CH3 is just tagging along. It's just, it's attached to oxygen, so it's just along for the ride. But you just want to recognize the bond making is to the oxygen, and the bond breaking is from the carbon. And whatever the R group is attached to oxygen, it's just tagging along. And then that would go on to make product. So O, and then CH2, CH3. And you would have potassium chloride as a side product, but you don't typically have to show that in organic chemistry. You just want to recognize that it's there. Okay, so if I ask you for the mechanism for this reaction, you would have to show the whole thing. You would have to show these arrows, making and breaking bonds. You would have to sketch the transition state, and then you would have to show the product. If you're just asked to sketch the major organic product, then all you have to do is sketch that, and you're done. Okay, let's take a couple of more molecules, a couple of more examples of reactions. Okay, let's take that reaction and that reaction. And let's again convince yourself that this is the characteristics for an SN2. So if we classify the alkyl halide, this alkyl halide is primary and allylic. And allylic is just fine. Allylic is great for an SN2 as well. But the point, so that's a primary alkyl halide, so there's not a steric problem, so this is fine to do an SN2. And that's RS minus, right? It doesn't matter what the R group, in this case it's a cyclohexane, but that's just tagging along. So the sulfur is the nucleophilic atom. So it's the sulfur that's going to attack this carbon, and the cyclohexane is just tagging along. And then you're going to break the carbon-bromine bond. So still have this carbon chain, but now that carbon is attached to sulfur, and the cyclohexane is still attached to sulfur. And then you would have potassium bromide as a side product. Okay, and in this example, so this would be a primary and benzylic alkyl halide, and benzylic is just fine for SN2. It actually enhances an SN2 reaction. but the primary, so it's not too sterically crowded, so this can do an SN2. And then the nucleophile, CN- is a good nucleophile. Carbon is the nucleophilic end of cyanide. So you're going to take, that carbon of cyanide is negative, that carbon is partial positive, so carbon's going to attack here and kick off the iodine. So now, so now CN is attached to that carbon, and nitrogen is just tagging along, and you would get sodium iodide as a side product. Okay, so that's some characteristics of an SN2, so we'll stop this video there. In the next video, we'll do some more characteristics of SN2 and do some more examples.